sets, like they graffiti everything.
Size awesome.
Yeah. They have these like anarchist skate groups that come and like draw like Antifa and like Anti-Sickle and everything.
Do you notice that you have access to all these grants?
Okay. That's better than what we usually get, which is nothing. Hey?
Sometimes people show us. We added a few more numerical specification required, and we are using it's a bit too crude to say something is 1 plus x.
Oh yeah, yeah. I remember there was some like log preview, like log 1 plus x.
Yeah.
I mean that's important stuff. Though.
Yeah, which is nice. I don't think it's using that. Pretty sure it's using 2 times speed, but somehow you can get the stabilization.
Good. I mean, the stabilization stuff is like on some year of Python. So I think a lot of types of models would just be trash about it.
Should we wait 1 or 2 more minutes?
As you like, yeah.
Yeah.
I have nowhere to be.
I have a feeling it's really like the gong is missing for lunch to tell people like
the bell, the school
time
bell.
for.
Yeah. I can go. You mean
Go scream in the corridor.
Scream in the corridor.
Say again? Yeah, please go ahead.
I regret
Just
that.
come over here.
That's right. Just start grabbing people.
Yeah. Maybe that's a job we need to do. Like at 5 before the session start, just go around and ring it out.
You should get an actual bell.
Maybe.
Yeah.
To bring the sheet.
I was at the conferences where people just,
Clap.
yeah, just leave them like hearing
Or call people
Can I
like
have
a dog.
kindergarten energy though? Like, okay, children, like line up now.
kind of works. Yeah, but
The bell is a bit PTSD inducing.
I'm just gonna show. I forgot to mention. I'm gonna show you the cards. With
Yeah,
the time
I saw
okay?
you had the.
I have cards,
Yeah.
sure.
So it's Ricardo and Jesse, right?
Yeah.
Thank you. Hello, everyone. We made it from lunch. I think some people are still doing. We really need a bell. I think next time you just go over to your session, just like, I don't know, ring a bell or something to notify others that it's time to go to the session. We didn't think about it now. So we have Jesse and Ricardo here today. Thank you for coming here. They're presenting recent advancements of, or the, say, successor to Piano, PyTensor. Give it away.
Hello. Yeah, we have the links here if you want to follow the slides. The one that will perish, but it's easy to type, and the one that will survive. So we'll talk a bit about the library we spend a lot of time in, which is PyTensor. You probably didn't hear about it, but you might have heard, if you're old enough, about Tiano. And PyTensor is a successor to it.
Spacebar.
What?
Spacebar.
Spacebar. Yeah, so just a bit about us. Jesse is doing a PhD in Paris, and I'm working, well, we're both working at PyMC Labs, a consultancy. And we have some hints if you want to find out where we live right now. And importantly for this conference, we are both core developers of PyTensor and PyMC, which is built on top of PyTensor, and a couple more projects. So for today, just a reminder, what was Tiano? It was, under the popular perspective, it was one of the first kind of popular deep learning libraries in Python. It precedes several of these, like JAX, Xarray didn't exist then. PyTorch, I think, might have existed at the same time. TensorFlow was inspired by Tiano. And he died or disappeared kind of 10 years later. And we think that, on the one hand, it's true, it was a deep learning library, but it was quite more than that. It was mostly a kind of library to do meta computation or meta programming with computational goals. And a lot of tools that are kind of unique, also made it a bit weird for users, but are quite powerful, and we think they are still useful today. Here I stole or print screened some Reddit thread when they announced Tiano was going to die. Someone that saw some of the potential there, they were sad that it was going to die because it was much more than just deep learning. It was, in his view, a complete symbolic math library that just happened to have convolutions and batch norms in it. And we do believe this is a good statement. So PyTensor kind of, we forked a library that forked Tiano, so it lives under us. And today we would draw the picture a bit different. We would put PyTensor above these frameworks because it's more abstract, and in the end we can actually compile to all the backends in the end to compute, but we work at a higher level of abstraction. And we'll try to make today the case why this is useful for researchers and also people developing libraries. So for researchers, mostly if you're writing numerical computation, which most people here will be, you want to be sure that you are writing performant code. And something that's more unique in PyTensor, that you are able to explore variations of your problem space a bit programmatically, not just write a function, rewrite it a bit different, but maybe have the tool that allows you to explore it automatically. For developers, which we are more than researchers, I would say, it's a really good tool to develop some framework that's kind of flexible and can be developed in a way that might be more natural for, if you have a astrophysics audience or molecular biology, you can write a library that allows people to be expressive in, let's say, natural language, and then convert that to number crunching in the end. So the story why we're going to motivate PyTensor today is users want to write some numerical code for their case. It might be just a generic logistic regression with some cross-entropy loss. You as a developer, you want to do something on top of these, but Python is not really rich for metaprogramming abilities. You would like to somehow have a representation that's more kind of boils down the computation that the user wants, and you can work on it. You can read it programmatically, obviously, and you can manipulate it for your use cases as a developer of a package. But if you just ask Python, what did I get from the user, you're going to get some, it's a function, not very useful. You can maybe get the doc strings if you are in an IPython and you could parse it by text. That's not going to scale well. You can try, Python has some tools. You can do bytecode parsing. Some libraries have chosen to trace, so you run user functions with dummy inputs and you just check what's happening inside the function. PyTensor and I guess Tiano, when they started, it was decided not to go with much of this magic and just kind of found a compromise where you say you can write code that looks almost like the one you want, but it's a bit different, and what you give us is already a nice representation to work on top of it. So the user the hardest thing is they have to specify kind of dummy inputs, what's going to be the inputs of the graph. Then they write mostly NumPy looking code. But we as the developers or the package that then gets these objects, we now have what we want to work with. So we have just we have a graph of the computation the user is interested in that we can start working on. We don't need to go a few hoops to get that graph. So everything we get from the user is like lazy. There's no number crunching yet. It's just placeholder variables that are strictly typed. So we know loss is a scalar float 64. It's a tensor type variable. You could have sparse variables. You could have symbolic slices. Mostly you work with tensor variables, which would be the symbolic alternative to NumPy arrays. And then you can start working the graph. So variables can either be root variables that the user defined, as you saw before, or they can come out of the application of other computations, of other operations. You get that through the owner of the variable. Then the owner can have an operation, in this case is the sum, with axis equals none, so all the axes get reduced. And from the owner, which is the application node, you can also ask what are the inputs that go into this graph node and what are the outputs. The outputs is the thing we started, the sum, and the input would be the addition term that was there. And you can just keep going up the graph, always getting these dummy variables, knowing their type and kind of the computation that underlies them. And you get that representation that I just showed in the beginning, that if you are doing metaprogramming, it's nice to already start at this level of abstraction. And then once you have a graph, what can you do with it? We have some examples here. You can query it, you can ask, does this graph contain X, does it contain Y? You can transform it for your purposes. You can obviously evaluate, and that's an important step. And usually you can do this in an iterative loop. Maybe you transform the graph a bit so you can query something about it, and then you transform it a bit more to answer different kinds of questions. And a big important thing is many of these tools exist in other computational frameworks, but they are usually not so pure Python. And Python really sticks with Python to make it easy to work on this graph, manipulate it, and do all these kind of steps. So I'll just give you some quick examples. First basic thing is you can query what are the root inputs from my expression. It's just something you might need to. But you can do more interesting things. So in our application in Bayesian inference, a lot of times you have expressions like log of sigmoid of something. And there are many variations of this simple expression that you can do numerically more stable. And we just show a simple example how easy it is to kind of query if this succession of operations exists in our graph. So you could walk through the assessors of a variable, and you can just ask, does my variable, my intermediate variable, come out of somewhere, or it's a root? So whether the owner is none or not. If it's not, does it come out of a log operation? And then, does this log have as input something that comes out of a sigmoid? Okay. And in our case, if you're running the notebook, it comes out that, there is a log. No, I cannot scroll. Doesn't matter.
Okay, yeah.
Yeah, we'll survive. Okay. Once you query a graph, you can try to transform. So as I mentioned, log sigmoid has some forms that are numerically more stable. And we just wanted to show that it's easy to just have a graph and modify a part of it, intermediate node. So we just iterate through our function that returns cases where there's a log sigmoid term. We get the X of that, and then we can do a graph replace. So we have the original expression the user gave us, and we just replace all the log sigmoid terms by minus soft plus of minus X, which is numerically equivalent, but more stable. And just to show that it works, now the graph has indeed the negative of the soft plus of the negative. We truncated it here. But you might not just want to rewrite equivalent graphs that are or equivalent computations. You might want to actually change the meaning of what the user gave you. So for instance, you could, for your purpose, want to add some randomness anywhere in the system, and it's equally easy to just say grab a node in the graph and replace it by it plus some, let's say, Gaussian noise. Or you could want to ablate part of the system. So how does the result change if some part of the graph is turned off? Here's just a cute example where we multiply by 0. There are other tools to do that. And other transformations you can do with the graph, you can do autodiff. This is baked in, I didn't mention because it's kind of trivial these days, but it was it was necessary for deep learning framework, so it was there from the beginning. You want to do efficient vectorization, so transform a graph that works on a vector like a time series, and now you want work in parallel on multiple time series. You vectorize the graph. Bit quantization is another kind of graph manipulation / ablation that you might want to do. And then when you compile these, or when you transpile a graph to something that actually crunches numbers, you might want to specialize for different backends. So your final graph might look different if you're compiling to code or chunks or anything else. Numerical simplification, that could elimination. Anything you might want to do in your workflow. And finally, once you, at the end of the day, you need to be able to crunch the numbers. And the reason PyTensor went to the top in our graphical representation is that these days you can actually ask to let's say, make your graph concrete into a backend. You can tell it, I want to evaluate it using JAX or number or C, and usually just a one keyword argument away. And we're just showing here it works. We have PyTorch, it's a bit more experimental. And the point is, we have such a simple abstract representation that's very trivial to execute different backends, especially with work that's being done to standardize how the APIs look across different libraries in the Python ecosystem. And yeah, that's where I would leave with this short example. I'll pass to Jesse, who will work out a more full example to give a flavor of Python.
Yeah, thank you. So my contribution to this is Ricardo kind of gave you the high-level overview of what is this package and why you'd want to do it. This is admittedly somewhat abstract, so we wanted to have more of an applied example. And we're going to take sales forecasting in kind of a time series environment as our example. And if that doesn't interest you, I don't blame you. But the idea here is to think about you're a developer of some package that has some purpose, and there's going to be domain-specific knowledge that's tied up in the types of things that you're trying to do. And so what PyTensor allows you to do in a very extensible way is to bake in some of that domain knowledge to provide more efficient computation to your users, and also to allow them to think in terms that they want to think in. Where we come from in the Bayesian language, or the Bayesian land, the most common example of this is log probabilities. Rather than writing down the log probability of your model, you'd rather think in generative terms and say, this is how my data occurs by some steps of random draws. And then PyTensor can automatically invert that process. Once you've defined your generative process, it can automatically say, given this generative process, what's the log probability of data that comes out of this? So the user is able to think in this natural space. So we're taking a simple example here of sales forecasting. The specific model we'll use is this Facebook profit type model. And again, this isn't super important. It's just to say that you have sales, which has these 3 time components in the front, and then it's a linear function of prices. And this beta coefficient should be negative, right? Like prices go up, sales go down. So our like quote unquote package, the purpose is you're going to give it a time series of sales, you're going to give it a time series of prices. It's going to estimate the relationship between these two using this formula, and then also do some post-estimation analysis with the more advanced features of PyTensor. So this is how it looks. Like Ricardo said, we have an API that tries to follow NumPy very, very closely, with the exception of having to define these root variables, which, I mean, if you're used to working in like SymPy, for example, this makes sense. You have to define like an sp.symbol. For us, you have to define a pt.tensor to start your computation. Once you have those symbolic objects, then you're just going to write down these formulas exactly like NumPy. And then once you're sort of happy and you know what your output is going to be, you're going to call pytensor.function, which will actually do the transpilation into some number crunching language. By default, the backend is C, but now, as Ricardo said, we're adding more and more backends. You can ask for it to come out in Numba, you can ask for it to come out in JAX, you can ask for it to MLX is a new experimental one we have for Apple Silicon, and PyTorch. So, okay, and this is just what the data that I generated happens to look like. So we have some price time series that goes up and goes down. We think of like sales or whatever. And then you have an observed sales, which is affected by the price, but also has its own idiosyncratic dynamics. So in order to do this, we're just going to use stochastic gradient descent. And all I want to show in this slide here is how we can call pt.grad in this cell 39, passing the parameters. So it's a quite nice natural autodiff thing. You don't have this like differentiate with respect to which argnum of your traced function sort of API that JAX has, or having to declare that this is going to require gradients like PyTorch has. And that's all because we have the graph that we're working with underneath. You just have some graphical computation. You say, I want to transform this graph from a forward to a backward with respect to these variables, and you get back a new graph. So this parent grads is a list of graphs, and then we can pass that into our update function. And then we'll pass that into SGD optimization, which just does stochastic gradient descent, and I've highlighted the details there. And okay, it trains, you can believe me, and we get some predictions. Fine. Here, the purpose is not to be correct, it's just to show you something. Now, there's a few points, so a few powerful things we get out of doing it this way. The first is the reusing of intermediate results. So if you had just written a function in NumPy, like a NP, like a define make prediction, you would have all these intermediate steps inside. Like what's the seasonality component? What's the trend component? What's the residual of the computation? And these are all of interest to the analyst who's running this package. In PyTensor, though, each one of these chunks of computation is itself a subgraph, and you're at any time allowed to go back and reuse these pieces. So, for example, I could create some decomposition function that also takes time, price, the observed sales, and the parameters, but then I'm going to return 1, 2, 3, 4, 5, 6 computations, and that's all of the components of the final output. So just automatically, I get back the decomposed time series, and you can pick out, like, this is the cyclical component, this is the trend component, this is the price component. PyTensor is also smart enough to compare across these graphs, so it's not going to duplicate computation. So to the extent that what is in the intercept graph also exists inside of the residual graph, it's going to compute that once and then reuse it everywhere that it can. So it's doing automatic optimization, it's doing automatic memory management. It's really trying to give you back the smartest computation that it can without the user having to think about any of this. Okay, and then this is what you get, right? This is this profit model with these discrete change points. So then another powerful thing is that we can go in and we can just modify chunks of the computation without having to redefine the whole graph. So this occurs again in Bayes when you have this quote do operator, where you want to say, I want to rerun my analysis, but conditional on some piece of it taking some specific value. So the example here is like, let's say that the Grinch steals Christmas one year and the cyclical effect goes to like 10% of what it normally is. So without having to rebuild a whole new function, without having to generate new basis functions to compute this season or wherever the season comes from, I can just say, take the seasonal term from index 150 to 200 and then just change it to be 10% of what it used to be. And then recompile this function. And then automatically you get this update. And whatever data you pass in, this is completely irrelevant. It would symbolically have multiplied by 10% on that data. So if you change it, you'll still have the same effect, just with a different line. So another kind of the most powerful thing you can do is to really lean into this symbolic algebra side of PyTensor and start thinking about how you can manipulate the user's graph in order to give back some other graph of interest. And my example here is going to be profit maximization. So you have this pi t, which in economics is profit, and the profit is the quantity that you sell times the price you sell it at minus the quantity that you made times the cost that you bought it at. Fine. And then you can set up an optimization problem and look for this P star. So I want to choose my price now such that I maximize my profits. And this is analytically tractable for certain choices of Qt. So remember that Qt here is a function of P. This was important in the beginning. We had that beta times price term in the model. And because it's linear, if you just work out the algebra, you'll get an expression for P star. So you have two options now. You could sit down and say, user, figure it out, push a pen, get this thing, and then compute it yourself. Or we could ask ourselves, could we take this profit graph that's derived from the model graph, could we somehow analyze the model graph and say, is this a linear model? And if it is, can we extract the graph for the optimum price just by analyzing what the user gave us in the first place? And that's kind of what we're going to try to do here. So the first thing I do is I write this find optimal p function, and we're just going to use a root finder. So like the really robust case that covers everything. No matter what you give me, I'll just use some Newton descent thing, and I'll find the zeros for this function, and that's going to be the optimum p. And it works. You get back something that looks like this. You make more than you used to. But you can do better, again, because we have this linear form. Okay, this is just showing that our profits went up. Great. Okay, so this is what if you actually push the pen and you get the math, you get this P star, and this is a well-known result in monopolistic competition, industrial economics, whatever. So the more interesting thing is we're going to do a sequence of rewrites on the graph. So way down at the bottom here in 64, I'm setting up the price. I'm taking the derivative of the price. And then I'm going to do a set of rewrites called canonicalization. And all canonicalization does, thank you, is that it says there's some standard form to put everything in, right? So expand terms, change subtraction into negative addition, things like this. So we have a standard form to reason from. We can add more rewrites. So here I distribute multiplication over substitution. And PyTensor has a very powerful and extensible language to write these kinds of rewrites. And then we just march through the graph once we have these rewrites and we say, can you find me this closed form solution? Is it linear and can you give it to me? And if it does, it gives you back a closed form solution. It says, yes, the price is a function of these two variables, A and B. And then from that, we can just directly compute that the optimal price is minus A over B. And you get the same answers when you run the root finder. So you could imagine an API where you have a lot of these types of solutions baked into your package, and then the user gives you some model. You march through all of these different options, and you say, well, you gave me something. Do I know what it is? And if I do, I'll specialize my computation in order to give you something better than just doing a numerical optimization. So kind of just in conclusion, Theano was unique. It rode this line between a deep learning package and a symbolic algebra system. It kind of got to be known as a deep learning package, but our argument is that what made it really special and really powerful was the symbolic algebra part. And so we're trying to lean into that and try to find new applications for it, including these rewrites, these optimizations, these stabilizations, and then this ability to do transpilation. So another example of an extension. Now we're working with named dimensions in this sort of tensor package. So automatic broadcasting. You say that you have some tensor with a user and a choice, and you want to softmax over dimension 1. What is dimension 1? Who knows? But now you can use this sort of X-array syntax, and it'll automatically figure out which dimensions you're talking about. And then also automatically broadcast mismatched dimensions if you're in that situation. And we have a small ecosystem that's sort of growing up around PyTensor, mostly the PyMC and the related packages, but then there's a few others that are creeping up. And we're sort of here to let people know what this is, why it's useful, and hopefully grow that ecosystem up. So yeah, thank you very much.
Thank you both. Any questions?
A question from my side. So now with this whole array API things, are there any plans to make this library play along with other arbitrary compliant plugins?
Well, yes, that would be great. We copy NumPy really, really closely. So actually, we were talking during the lunch break that it shouldn't be too huge of a lift to get us there in terms of API compliance. Do you have more thoughts?
So there's some trickiness where most of these libraries that are being adopting the framework, they are eager libraries, or they are not really symbolic or lazy the way that we are. So some of the things we talk with them, some of the things are hard, but 99% of the way we want, and we actually want that. So I think it's time for people learning Python not have to learn the tiny chords of different frameworks. And we try to sit there on the top and say you can do every. We definitely should offer that, and yeah, something we are pursuing.
And another question which has not been very clear to me, but what is the status of the GPU support? Because it seems like some things work, some I'm not so sure.
Yeah, so back in the day, Theano had its own GPU framework. That was hard for us to maintain, so we just cut it all. So we cut our code base by 90%. These days we lean on other libraries that offer GPU natively, so if you compile into JAX or Torch, you can just use GPU as you would use through those libraries. Number would require us to kind of re-implement it ourselves, but we offloaded that to the more number crunching libraries, and we try to keep it just light and focus on this abstraction of the graph properties, and then let you get out of the way once you want to use your GPU or parallelize across your hundreds of CPUs, things like that.
So there's no OpenCL?
No, we don't write our own GPU kernels.
Okay. Yeah.
If you have funding, we'll do it.
He will do it. I don't think we should. No, that's changing very fast, and there's big money being thrown at that. I don't think it's where we can get a competitive edge.
Okay, then thank you.
Thank you.
Bist du eigentlich Janos oder Janusz? Janusz, okay.
So you kind of have to find someone to share castle.
It's ready. room looks full. I hope you're not too tired. We have Janusz here again. Thank you, Janusz, for joining us. He's going to talk and actually not do live coding, which is, I guess, better for him because this is to help microphone. He's going to rewrite OptiMagic from scratch in 30 minutes. So I would say time is running.
Okay, hi, I'm Janusz. I work at Applied AI. And since we have plenty of time today, I'll start with a few announcements. So if you join us at the Applied AI booth right out there, you can win a mechanical keyboard. You just have to answer a simple Python quiz, or actually not that simple, but a Python quiz. We don't collect any personal data, it's really just about giving away a keyboard. And also, we are hiring, so if you want to come work with us at Applied AI, small non-profit in AI research and education, we are looking for a research engineer. Right now, you can also talk to us and apply. I'm not sure if everyone here knows what OptiMagic is. I'm the author of OptiMagic. OptiMagic is a library for numerical optimization. And it's basically aspiring to be a complete superset of SciPy Optimize, and you want to extend SciPy Optimize in two ways. One is you have way more algorithms you can choose from, and depending on the problems you're solving, it's really important. And the other one is we are adding convenience features like diagnostic tools, error handling, and more. But by now, OptiMagic is quite big, so it's a bit hard to understand how it all works in the background. But we're kind of proud of our extensible architecture. So recently we participated in Google Summer of Code, and it proved to be really easy to add new algorithms. So the idea is that now that I created OptiMini, it's a tiny version of OptiMagic, with 300 lines of code written in an afternoon, and it shows the core ideas of OptiMagic. And that's what we're going to walk through now. So more specifically, we want to create a wrapper around SciPy Optimize, so that's how we start. And then first we want to add labeled parameters. That's maybe going a bit in the direction of previous talk, also it's sometimes nice to have names of things and not just position 3. Then we want to add history collection. That means after you ran optimization, you can kind of see how it went, and if you ran 2 optimizations, you can compare how well they went. And then we slowly start developing the extensible architecture. Extensible means 2 things. One, we can add new algorithms without touching their source code. And 2, we can add new algorithms without touching our source code. So it's just newly added code to implement these algorithms. And then in the end, I kind of show that this works by adding an optimizer that's not from SciPy, it's from NLOpt, and I show how it integrates seamlessly. And all of this is not production code, it's the simplest possible implementation of things, just to show the core ideas. So, if you want to follow along, you could scan the QR code and look at the pull requests. They are in the same order as I'm going to make these changes, so if you prefer to look at a diff and not at code on the slides, you can follow there. But first, a very quick recap on what is actually numerical optimization. So numerical optimization means we have an objective function f, we have some kind of start parameters x0, that's typically a vector, and then what we want to find is the argmin or the min of the objective function. And a super simple example that's depicted here on the right would be that f of x, like the objective function, is just sum I xi squared. How does this work in code? You can import a minimize function either from SciPy or from OptiMagic. Then you define your objective function as a Python function, and you pass that function and the start parameters to the minimize function. So simple enough. In SciPy, for example, this x0 always needs to be a flat numpy array. So then if you need to take your parameter vector apart into single quantities, you need to do that by position. So that's the third thing we want to change. So we want more flexibility for the parameters. We want a minimize function that behaves just the same as SciPy. So you pass an objective function and parameters and say which optimizer you want. But now this objective function does not have a flat array as the first argument, but it can be an array or a dict. In our case it's a dict, and then it returns float, and my thing is we have names for the parameters inside that function. These functions can get quite complex, so then it really pays off to have names. And then also the start parameters are the same dictionary format, and also the result after running the optimization will have the same format. And again, we absolutely do not want to touch the source code of the optimizers we are wrapping, because they might be in Fortran and in C, whatever, we don't want to touch that. How do we do that? So we want to hide the dictionaries from the optimizer, then we need some kind of converter to convert between formats. So the optimizer needs flat arrays, we have dictionaries, so what do we need? We have a converter class where we first store the original part, so we know the labels, the keys. And then we have a simple flatten function and an unflattened function. It doesn't really matter in which order we write things, as long as these are inverses of each other, that's enough. And then we need to write a wrapper around the objective function. So we call this the internal optimization problem. Again, we just store a bit of stuff here in the init method, and then we implement fun. That's now taking an array and returning a float, even though the user function needed a dictionary, and we do that by simply calling the conversion. And then the last thing we need to do is we stick this into a new minimize function. First we do a bit of we create instance of the class we just created. Then we create a flat x0 now that we can pass to SciPy. We call the actual SciPy minimize function, do all the optimization, and then we convert the result back into a non-flat format and pass that to the user. So we achieved our goal of we can now run optimizations where the parameters argument is not a flat array. That was simple enough, just a simple trick. So now let's add a bit more features to our optimizer library. Next thing we want to do is adding optimization history. And to make this goal a bit more tangible, what we really want is some plot like this. So you ran maybe one or two optimizations using different algorithms. You don't really need to know how we choose these algorithms, just there are a bunch of them and you want to compare how well they perform. And then you can actually do that in a plot. And if you don't have this plot, it's really hard. Like you can maybe look at some iteration counters, but that's not so easy. So, and we want this history collection to be automatic and want to have a simple plot function to visualize it. And again, we don't want to touch the source code of the optimizers. And I think by now you can already guess how we're going to do. So, any ideas? We're also going to stick it into the objective function, so into our wrapper of the objective function. So we start by creating a super simple history class where you can just store the function values and the parameters that the optimizer is exploring. We also now need a new optimized result that actually contains the history, so this is just the setup. And then we change two things we already had. The internal problem now also has the history, and each time after the user-provided objective function is evaluated, we simply append to that history. And then in the minimize function, we also, just after the optimization, we add the history to the optimized result. So again, this works really easily for any optimizer. Now, this simple implementation will not work for any optimizer that parallelizes using multiple processes. We found a way around that in OptiMagic, but you would have to look into the library to see how that works if you're interested. And then maybe let's do a quick demo. How can we do that? We run this simple optimization. And we actually get the history plot out, so it works really nicely. This was the kind of simple part of the talk where we just do a few tricks to get a few extra features into the optimization. Now we talk about the more extensible architecture. This is going to be slightly more abstract, but also not too hard. Let's first look at what is the actual problem that we have. So we want to create this minimize function, which is a wrapper that hopefully can call many, many different optimizers from many, many different libraries. But now we have the problem that we started with SciPy, and the syntax of the library we are wrapping is actually showing up in our core logic, so in our main function. And that means each time we add another optimizer, we need to change the minimize function. Also, it would by now, like all these optimizers support different options, so by now it would be really hard to validate which option is supported by which algorithm. And if we want to do this here, we would need a lot of if, elif, else, and we don't want it. So in order to solve this problem, we're going to introduce a simple abstraction, and it's your abstract base class called algorithm, and it has this abstract method called solve internal problem. The method takes the internal problem where everything is in NumPy arrays and really easy and really close to how most optimizers expect the stuff anyways. And then we also return from that method just an internal result that, for example, does not need to know about the history, because all of that is going to be added somewhere else. And the interface of this algorithm is deliberately extremely minimal, so we don't want to prescribe anything of how these algorithms are implemented. They can be in a different language or whatever, they just need to be able to be converted to that interface. And also this algorithm, I think it mostly acts as a protocol here, so we use inheritance, but we don't use it for code sharing. We actually just use it as an interface that, to make our code simpler. And then let's look at an example of how this algorithm interface can be used. So we add the LBF-GSB algorithm from SciPy here. We first list all the options, including type hints of all the that this algorithm supports. And the nice part is that this can be used for validation then. And then we write the solve internal problem function. It starts usually by a translation step, so we choose nice declarative names, nice expressive names for all the options, whereas many of the libraries, especially those implemented in Fortran, they use like 8 character at most names. So we can have this translation step. Then we call the actual algorithm in whatever syntax it needs and return internal result. And now all of the algorithm-specific syntax is encapsulated in our internal algorithm. How do we put this into the minimize function? We start by creating a simple registry of optimizers that's here just a dictionary, and then we can create an instance of the algorithm, call the solve internal problem method, and then in the end process our optimized result. And this means that by now the minimize function is fully agnostic to how the original library that we are wrapping works, so we don't need to change it anymore if we want to add more algorithms. However, there is this is not complete. There's a small problem, and that is algorithms are way more different than this picture showed. So for example, you might have some algorithms that support box constraints on the parameters, i.e. lower and upper bounds. Other algorithms need or support using all kinds of derivatives, gradients, Jacobians, hashings to speed up the optimization. And some algorithms also support constraints. So that means that we need some kind of way of how algorithms provide information to OptiMagic that we can then use to process the user inputs and maybe also validate the user inputs. How do we do that? We do it using a really simple decorator approach. That means when you implement your new algorithms, you decorate it using the mark minimizer decorator, where you can give it a name, and in the actual OptiMagic, there are way more options than this, but here we can use to communicate whether this algorithm, for example, supports bound constraints, or it actually requires bound constraints like global algorithms typically require. And this decorator approach introduces a very nice visual separation of what are the algorithm-specific tuning parameters and what is just metadata. It's also really intuitive for new contributors. How can we use this additional information now? We can now, in the minimize function, do checks on the user-provided inputs. So we can, for example, if you request an optimizer that does not support bounds, but you have bounds, then you can raise an error and can have a good error message. And the important part is that this is possible without keeping lists that would have to be extended each time a new algorithm is added. It's simply based on the properties that you specify, based on the metadata that you specify with the algorithm. Okay, so now we have an extensible architecture. Let's test it. Let's add an optimizer that looks very, very different from how SciPy optimize works to see if this actually works. How do we do this? Again, we use the mark minimize decorator. We create our data class inheriting from algorithm. We list all the options. I just listed two, but there are many, many more actually. And then we can implement the solve internal problem method. And you can actually see, so an opt expects the objective function to be in a very different format, having actually a second argument that's sometimes used to pass an additional output somewhere. And also the way of setting options is very, very different, more object-oriented here. And also the result that you get back from the optimization is very different. So even though the library is very different, it's not hard to stick all of this into this very simple, common algorithm interface. And then, if we now use this, we will automatically get the features that we implemented in the beginning, the history collection and the flexible parameter format, because all of this is hidden from the optimizer anyways. So let's try this out. Hope this works. So yeah, we should now have basically same example as before, but we also call our new optimizer, and then we will run this. It doesn't work. I need to restart the kernel probably. And it does, and we now see that okay, there's a third optimizer. Even though it's implemented completely differently, we can nicely compare it, and it actually is also the fastest optimizer on this problem, so nice that we have it available. Just a quick recap. So again, if you want to read more into this and see how it's implemented, I didn't show all of the code, but a subset. You can go into this Optimini repository, and we implement in 5 pull requests what we just did now, and there you get the complete code. So we first introduced the label parameters. We then added a simple history collection. We implemented the internal algorithm interface to make our package more extensible. We added support for bounds and implemented a decorator that can be used to communicate between algorithms that are wrapped and OptiMagic, and we finally added an algorithm from a completely different library. Is this all there is to OptiMagic? No, it's not. OptiMagic is a bit more general than this. So in OptiMagic, for example, we have even more general parameter formats. For those who've worked with JAX, they know maybe the PyTree format, which is just any nested dictionary, data class, whatever, arbitrarily mixed and nested, you can use as parameters. We have by now a lot of optimizers, for example, recently gained support for narrow grad, Bayesian optimization, and gradient-free optimization library. We have history collection also for parallelized optimizers, and we have a lot of parallelizing optimizers with persistent logging, error handling, parallel numerical derivatives, multi-style, and a lot of other features. So if you're doing any kind of nonlinear optimization, you can try it out. And it really, for the basic cases where it's just like sometimes minimize functions, then you might not even have to adjust your code if you don't need the advanced features. That's it. So I'm open for questions.
Thank you. That was fast. Are there questions? I might have one. Oh no.
Yeah, thank you for the talk. It's very cool. I guess I have two. One is very trivial. Are there progress bars for any of these?
We don't have progress bars currently because most of the optimizers have adaptive convergence criteria, so we really don't know how many iterations there will be.
Sure, just something I can feedback while it's running.
We do have like logging, and you can even look live at these plots and see how it's going.
My other question is more real. Is I'm thinking about optimization libraries where setting up the problem is less trivial than just passing a Python function. I'm thinking about like CVXPy for these like conic quadratic optimization. Is there any hope of getting something like that into this framework, or is it just too different?
So we don't do linear programming and these very structured things, and I mean there are nice modeling languages for those. So currently we don't have any support for that. What we are thinking about adding is in hyperparameter optimization, you typically also have a very different way of specifying your search space, often with discrete options. So we're thinking about adding some of that, but currently it's like SciPy's minimize function, just continuous dimensions.
Then a not like technical question, but what did you learn while rewriting Optimagic from scratch?
So first of all, I wondered why did it take us so long to write Optimagic if like you can get quite far so quickly. And also I realized that basically we have only been applying the same ideas over and over again, and each time we stuck a bit more functionality into this internal objective function, and that's really powerful. So I hope what you're taking away is if you have any problem where you sometimes need to switch between libraries and you don't like how a library works and you are tempted to implement all the algorithms from scratch so you can give them the interface that you want, think twice whether you can maybe just write a wrapper around them and not touch all the numerical code and just make the stuff behave a bit nicer by somehow finding one smart way of hooking into things.
Thank you.
I can also speak up. Hey, thanks. So it's actually quite a beautiful design, I would say. So I have not seen a similar package in the Python world that is trying to wrap multiple packages using a very systematic framework. I think it's extremely common in the R world to have the most popular packages there are called marginal effects and model summary. Did you take inspiration from these packages? No, there's also marginal effects clone in Python. But from design, are they similar? Have you ever looked at them? Okay, I think there's some similarity in the Python package and in approaches.
So no, I have not looked at them. I would hope that this approach becomes a bit more popular. I think it's also a bit more popular in Julia to have common, so they also have a common optimizer interface that everyone tries to adhere to. And we hope that, at least for optimization, this kind of gets established now, because I mean, if you implement Optimize, you can just give it this interface. You don't even have to make it part of OptiMagic, and you can still get all the benefits. So I hope this becomes a bit more prominent in the Python world.
This is maybe a bit of an evil question, but obviously now with the benefit of hindsight, you were able to present this very nice design.
Mm-hmm.
How much of that design did you have in place when writing OptiMagic initially? And how much of that kind of grew organically?
So almost zero. OptiMagic really came from having a problem, not having a good idea for a solution, and I was also a really bad programmer at the time. I really just wanted to solve the problem. So the idea of we started now is flexible parameter formats, and I found a way to stick this into an objective function, which was not so nice, but it worked. And then we had a few actual design iterations, so where we took time to see what worked, what got complex, and then came up with a new design to make it simpler. And that's how this was in the end created. But as I said, like now in hindsight, it seems really the obvious way to do everything. So yeah.
Thank you.
Okay. Let's say everything was good. Thank you.
Thank you. Really nice talk.
Thanks.
I think it's good to talk about these high-level like design thinking more often.
Yeah, I mean, especially if you are. I mean, I come from economics. We don't even talk about programming. Like something everyone is supposed to learn on the side.
Yeah.
But if we talk about programming, we don't talk about design or software architecture. We talk about how do you get the thing to run.
Yeah.
So.
Astrophysics background for me, but yeah, the same. It's like, how can I get this to run?
Yeah.
I never learned anything about like how to design a system like that.
Yeah.
So you pick up these design patterns over time, maybe, but
Also, only when I started working with my colleague Christoph is here, he has a bit, actually also not like formal training, but he had a nice co-worker with simple software design, and then I got names from many of the things that I was kind of rediscovering, and then I knew the design patterns. Yeah.
really nice. Thank you.
See you.
Hello.
Hello.
Sorry, I'm in session chair. Do you have Francesco?
Yeah.
Okay. Everything working?
Shall we wait 5 minutes?
Yes, definitely.
Okay.
This microphone didn't really work well. I would recommend to have the handheld. Does it work for you? I think you have to turn it on. Outside.
Right.
There's a slider down there, like here. You just
Right. Oh, I see. Hi.
Hi?
Yeah.
Perfect.
Perfect. and MatchPy and building an integration somehow?
Yes.
Okay.
Yes. That is. Well, that is it.
All right. Nice.
Is it? Will it be available on YouTube, right? Or
I think it's, as far as I'm informed, it's currently streaming, live streaming on YouTube. I hope we have the videos afterwards, but last year it was a mess, so I won't promise.
yeah, I didn't find the ones of last year.
Yeah, last year we had, we were quite understaffed last year and we had a problem with the video setup. So essentially we had video files and audio files and they were all separate and we would have needed to manually fuse them together, which was painful.
For now, the recorded sessions from like 2 days ago are available. So we should be fine.
Okay, perfect.
I'm going to show the signs. Sitting here, I'm going to show you the signs.
So I have 15 minutes plus 5 for questions.
Exactly. That's how I would say it.
I'll also put a timer.
Ah, well, okay. This happens. Just
Okay,
don't touch it.
Shouldn't touch the.
This is annoying. We've had problems with the setup at some point.
Someone joining?
Well, yeah, I mentioned before we need a bell between sessions so that people know when it's time to move over.
Okay.
Hello everyone. You're just one talk away from your coffee break. I hope you give this talk full attention. Francesco is here today to talk about an experimental integration project between SymPy, symbolic pattern matching, and was it MatchPy?
MatchPy, yes, exactly.
So thank you. Give him a warm welcome.
Hi. Okay, hi everyone. I'm Francesco Bonazzi. I work for Intesa Sanpaolo Bank in Italy, but I'm also a developer of open source software. In particular, I have been working many years for the SymPy library, and I want to show you in this talk how we integrated the SymPy and MatchPy libraries. So, what is SymPy? SymPy is a pretty famous library. It's a library that allows people to do symbolic mathematics in Python. Think of it as something similar to Wolfram Mathematica, but fully open source and fully in Python. So, as in this snippet code example, you can see that you can import the SymPy library, define some symbols, and create mathematical expressions and visualize it. You can take this expression and call some algorithms that SymPy provides. For example, this expression in the x variable is a second degree equation. You can solve it and get these two solutions. You can derive it by in this example, by the y variable. You get another resulting expression, or do something more complicated like integrated the variable z. In this case, you get a pretty complicated expression because the result of the integral also depends on the value of the y. In this case, you see this mess because in case the y variable is a plus minus imaginary unit, the result is different. This is just meant to show you that how far SymPy gets with these implemented algorithms. So, how are expression formulae represented in SymPy? Well, the point is like a formula, unlike other libraries where you put numbers and you compute them immediately. The formula is held in a frozen mode, and it's represented by an expression tree. Here you can see the example of a simple expression: a times cosine of a plus b plus a squared over b. And in this, on the right, you see the graph that represents how internally this expression is represented as an expression tree. So, what is an interesting stuff that you can do at this point? Because you usually, when you have mathematical formulae, you're interested in transforming them, do calculations. Calculating on the symbolic level means transform the expression tree into another one. So what you do, you can implement algorithms in a traditional way, like tree traversals, but another interesting approach is pattern matching on expression trees. Here we see an example. I'm just using some letters, but in the upper row you see a representation of some trees in a functional way, while down you see the graphical representation. On the left one we see an example expression tree. In the middle we see a pattern where A is meant to be a wildcard, that is, should match some expression. And we see on the right side the match in the original target tree on the left side. So we can do pattern matching. It's a bit different than regular expression because when you use regular expressions, you don't have you cannot count the number of parentheses that you open. So they're limited. This is something more advanced that you need. So what else do you need for mathematics? Well, we need the associative property and the commutative properties. If you have the expression 1 plus x plus y, as in this example, you can have a simple representation, as in middle one, where you just have a node, addition node, and the 3 addends. But you can also have 1 plus x parenthesis plus y, and the expression tree is structurally different, or 1 plus x plus y parenthesis, that's also structurally different, but mathematically equivalent, as well as the commutative property, which means that you rearrange the children of the node in any way, the expression should be mathematically the same. So this is another thing that we need for pattern matching in mathematical formulae. So this is an example. If I get the expression 1 plus w, where w is the wildcard, it should be able to match all of these sub-expressions, the one in the green squares. You can see the difficulty that this implies. So how do we do it? Well, here comes the MatchPy library. We were actually working on the SymPy library on a project about some advanced matching, and all of a sudden these people published a paper about their research project and they created the MatchPy library. And it was exactly what we needed. It was an associative commutative pattern matcher, and especially one very nice thing that they were doing. They were creating a system where you can take many patterns, create a unique data structure called a discrimination net that performs many pattern matchings against the target expression at the same time, and thus accelerating a lot the matching, the pattern matching process. So we just contacted these researchers and we started collaborating with them on the integration, and given the huge potentials of making SymPy and MatchPy work together. So let's see an example. Let's build a simple equation solver. But this is just an example because SymPy already has an equation solver that works pretty well. So just if you need it, just use that one. But this is just an example a simple example to show you how this interaction works. You can create an equation solver by using patterns. Here A, B, and C are wildcards that should not match expressions containing x, and these are usual equations and their solutions. So how do we do it? Well, this is an example Python code of how you do this connection between MatchPy and SymPy. We import this MatchPy connector submodule of SymPy. The important objects are the replacer and the while dot. Then we proceed creating an X symbol, standard X SymPy symbol, and 2 while dots that are the expressions that are supposed to match the sub-expressions. There's an additional property, optional. When you declare optional, the while dot is optional. That is, it will match even if in the expression tree the wildcard is not contained, giving that as the default value in case of no match for just the wildcard. I'll show you later why this is needed, how this is useful. Then we also have some constraints which are just made to make sure that these wildcards don't contain X. The custom constraint is you just pass a lambda and that should return true if the match is valid or false if it's not valid. So you don't have to, the matching suffix trees don't have to contain X. And then we start creating a replacer. Here is a simple example of a first degree equation. So let's try it. And it works. I mean, we see a complicated spread, a simple first degree equation in X with some complex expression tree. And you see that red is the X variable, Y is the A wildcard, while green is the B wildcard. above is on the extreme right is the targeted matching pattern that was created in the previous measure, and we see above the complicated expression. Below we see a simple expression, x plus y equals 0. In this case, we can see the optional argument coming into operation. Technically, the expression tree is different. It's not the one, not compatible with the one of the pattern, but luckily, MatchPy has the possibility of declaring some nodes as one identity, which means if the node only has one argument, it should be equivalent to the argument plus the fact that we added an optional value to the A wildcard allows it to understand that it can add that this tree should match this expression and add the optional value to A. If we try to solve an equation that was not in the pattern measure, like cosine of 2 times x equals 0, it would not match, but we can add another rule to the replacer. Just adding a rule and clearing the cache actually can show that the equation will end up working. So another project that has been really the motivation of this interaction was bringing the Ruby roots into SciPy. Ruby is a project created by Professor Albert Reich in Canada about creating about 5,000 pattern matching rules to perform a symbolic integration, and he claimed he was able to outperform Wolfram Mathematicus integrators by defining all of these kind of rules. So there's an ongoing porting, and it's been quite a cumbersome project. So what is the current drawback of this approach? The point is MatchPy is very efficient at when you could have this discrimination network created. That is, once you load 5,000 rules, you're pretty fast at matching against the target. That is, you match all rules at once in a single time. Unfortunately, loading the rules is pretty slow. So every time you add a rule, the data structure that actually performs the matching has to be updated. And this is unfortunately currently a pretty slow process. We tried to, together with the MatchPy authors, we actually found a solution as a workaround by creating a code generation. The MatchPy has been added the ability to generate a decision tree out of this structure, just a code generator. And we also did an experimental port of this decision tree generator into C++ with the Sim Engine project, which is, let's say, a rewriting of the core of SciPy into C++. Both, this is really experimental, it's not really ready for usage, but hopefully it will eventually. So, and that remains with what we would like to do in the future. That is, we would like to, this not, we would like to work on to bring this code generation to fully work, basically. And another thing is that would be needed is to do some rewritings of the MatchPy library itself, because there's a defect right now whereby expression trees need to be classes of the MatchPy library. So some rewritings to allow a more generic tree traversal would be much desired. So that was it, and thank you for your attention.
Hello. Thanks. Any questions from the audience?
Thank you for the talk. I'm not sure I really got this with the discrimination net. You said that it's a special structure that allows like matching all the patterns at the same time. Can you explain a little bit more how this works? Because I mean, I thought like every time I apply a pattern, of course something changes then. But how is this practically done?
Okay. The idea is that you have many patterns. The easiest way you can match them all is just write a for loop and start first pattern, second pattern, and so on. What this algorithm actually does is that it takes the patterns and watches if they have a shared root. It analyzes the tree structures and sees if some patterns have the same root or beginning, and then they get fused together. They get like fused together into let's say a multi-pattern. I mean, if the both of the patterns are additions, have an addition as the root node, you already know that the first node is the same for the both. So just write addition and then separate them later. For example, look at this picture. This is taken from the MatchPy paper. Here you see 3 patterns. It's matching actually a list. In one case, it's matching a list where the wildcard is the first element and 0 has to be the second element. In the second case, it matches a list where 1 is the first element, and then there is a, let's say that let's say a wildcard that matches many elements. And the last example last pattern is just a list where only the number 1 is present in the list. These are 3 patterns, and you see the expression tree. This is the discrimination network that gets generated. I mean, the first, the root node is the list. Now it's a square bracket being open. Then you get the first separations, first split. 2 patterns have a need the first argument to be 1, while the other pattern needs the first argument to be y. And then the lower splits again, because the other one pattern is just this should match just the one element list, while the other one needs to have another wildcard. So once you test it against another list, you just have a walk over a single tree.
Okay, got it. So you can way faster rule out the second rule if you're already like in the path.
Yeah, you mix similar patterns together, and so that you need to walk just one expression tree to match it instead of trying many. That's the power of MatchPy.
Okay, and then maybe a second question, if I may. I mean, what a compiler does,
generates the code. I mean, in this case, it would generate the code if a nested list of if expressions.
Yeah.
If the first element is a list, if the node is a list opening, then the second there's if, or if it is 1, or if it's not 1. I mean, there's like this, it goes on like this. It's a bit complicated when you have commutative property, because you have to have like some lazy looping around all the combinations. The associative property is also a bit more complicated, and the one identity is also pretty complicated. I mean, there's some complications. I mean, it's not easy, simple, but the algorithm actually is robust.
Okay, and could it then also help other projects like LLVM to speed up or do more optimizations?
Yes, potentially yes. Okay. Then someone would need someone taking out the code and porting it there.
Cool, thank you.
There's another question apparently.
So you nicely showed how to combine SciPy and MatchPy, but I'm new to both, so I tried to distinguish what feature comes from which package. And I assume the replacement word is something that's built into MatchPy.
Yes.
And the thing that you have on the left with the operation, is this something also from MatchPy? Or is it
This code in the slide is just MatchPy.
Okay. So MatchPy provides the associated...
Everything, the algorithm. SciPy is just the symbolic engine. We have the expression trees, the order types, etc. It has also its own algorithm. It actually has its own much less powerful pattern matching engine, which is much less powerful, but the one integrated into SciPy. The point is, if you use this connector, you kind of trickish tell MatchPy that SciPy expression trees how they should behave and how MatchPy should traverse and the expression trees of SciPy, which nodes are associative, commutative, one identity. It sets up everything in MatchPy to do tree traversals of the SciPy expressions. Once you've done that, you can use MatchPy with SciPy expression trees. MatchPy has its own expression trees and tree traversal strategies.
Okay, thank you.
So I think we run out of time. We can find fridges for later at the coffee break probably. So thank you again for presenting, and it's time for coffee.
Polish?
Me?
Yeah.
No. Why?
I thought you may be Polish because you're helping.
Because I'm happy.
Helping.
Helping? Oh no, I'm organizer.
Oh, you're organizer.
EuroSciPy organizer, yes. But I'm not Polish. I'm from Germany.
Oh, from Germany.
Yes. Where are you from?
Mexico. This year is smaller, right?
It's very small. It's we have really had like not as many. How do you call it? Organization committee was really small, and also participants. But I think like participants in the talks were more than in Szczecin. I'm not sure. I'm looking at the official numbers, but it seems small, right?
Yeah, because I was in Basel, I think 3 years ago.
Yeah, I think Basel was larger. So I wasn't there, but people told me that Basel was way bigger. So somehow numbers declined. How do I get this in here? Works. So wait, what's your name?
Horacio.
Horacio? Nice to meet you.
Nice to meet you. Are you a researcher?
Yes, I am currently doing my PhD at the LMU in Munich.
Oh.
Yeah.
Which topic?
Finding out still. I've worked. I did some work on trace clustering. Essentially developing algorithms to cluster traces such that they don't have to be encoded in in a lower dimensional space, which is interesting because traces, like event traces, I don't know if you're familiar with data structures, like you have, I don't know, event A followed by B followed by C, 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 C. It's a bit different data structure than, I don't know, for example, graphs or for, I don't know, numeric data. And yeah, so I could go on, but this was the first approach that I did. And then let's see where I go from there. I hope that I can still move into a bit of like graph machine learning. Let's see. I'm not sure yet. Still finding my topic.
Oh, interesting.
What are you working on?
I'm building a SaaS product that converts natural language to SQL queries to search in your data.
Oh, cool. Yeah. You said on your how's it called, badge, it said you're a freelancer. Are you a freelancer?
No, not really. I don't know why they put that.
Okay, interesting. Yeah. Something got messed up, I think. Also, like mine wasn't really. My employer didn't show up on my badge. I don't know. Yeah. So I need to set up the light.
So you live in Munich?
I live in Munich. Yes. Where do you live?
In Mexico City.
Oh wow! So you traveled from far ahead.
Yeah, but I mean, I was just like a month holiday.
You're on holiday, okay? So
yeah, summer
stepping
holiday.
by here, okay. Yeah. Nice.
Because last time I also was at holiday and I found about it.
Mm-hmm.
So I went.
So this year again, nice.
Yeah.
So where are you going to? Which places?
No, I was in Lisbon.
Nice.
Madrid, Barcelona, Paris, Amsterdam.
Nice.
And Berlin.
Yeah. So all the city trips.
Yeah.
Cool.
And last time I was at Munich when Munich, Hungary, and then I went to Czech Republic and then Basel. I think.
Oh, nice. Okay. So from east to more like west travel direction.
Yeah, I'm coming back Sunday.
Oh, cool.
Yeah, but I found some other conferences for product, and they're in Lisbon and Berlin, I think. I think there's a bunch of product conferences in Germany.
I guess so. Like Berlin is a huge hotspot for developers and startups and so on. So I'm not like into it. I've just done PyCon and give me a second. PyCon and PyCon, like EuroSciPy and PyCon.de. Those were the conferences that I organized and attended.
Oh, you organized EuroSciPy?
Yes, last year. Also, yes. Last year we were in Szczecin, also in Poland.
Oh, yeah.
Yeah.
So next year is going to be here also?
Yes. Next year we're going to be in Krakow, and then we're going to switch probably location again. But we had to switch in between, and this is, I think, like after doing one setup round, because of like the things that the logistics and whatever, it's good to stay like 2 years in a row, so you don't have to do everything from scratch again. That's why we're going to stay one more time, yeah. Sorry. Okay.
So, but how do you organize? Is there like an organization that does that?
Yes.
That you belong to?
Yes. If you want to join, you can just write us an email. If you want to help out organizing, we would be happy to. You can just write, I think, on our website there is an email. I think that's the best, because then everyone gets this email, everyone can see it, and we can just reply. For now, of course, the main part of work is done. And I guess it's going to start again in a couple of weeks, like I would say winter this year. Probably like August, September will be a break, and October, and then we're going to start again productive from November, I would assume.
Oh, it's a lot of work.
It does. It definitely does. It's like also this year we were understaffed, so...
Oh, you were understaffed?
Completely.
Oh,
yeah,
okay.
Completely. That was a bit of a problem.
Yeah, you look a little bit tired.
Yeah, it is. It was not my plan to be, for example, to do session chair just now and everything. It's just like jumping around and helping where I can right now. Okay, I just need to find a colleague now to get set up. Are you enjoying it?